All right, let's go ahead and continue where we left off in the last video, talking about force and acceleration. So I had mentioned what we know from the first law and trying to get to the second law of Newton's laws. And I wanted to talk about this diagram real quick. So this is showing you a person in their car with two people trying to help push the vehicle forward. And so we have two forces here from the two people pushing on the car. We have a frictional force from the pavement. And we have an overall acceleration of the vehicle to be pushed forward. Okay, so with all of that information, we're able to create a free body diagram here. And we can do the same thing when that vehicle is being towed. So again, we have some sort of acceleration here, result acceleration. Excuse me. We have the same frictional force, but now we have a different force of the tow truck. Okay, so we don't have the people pushing on it anymore. We now have the total force from the tow truck pulling the vehicle. So we can see now that there has to be some sort of relationship between acceleration and force, okay, and also with mass. Okay, so let's go ahead and continue here and give you that relationship with Newton's second law of motion. Excuse me. So it basically states that the net force on an object is equal to its mass times its acceleration. Okay, and this is in vector form. We can also write it in scalar form here. Okay, and this is an example of maybe a little bit more clear. Say we have a basketball player and he pushes a basketball forward with some force, okay? The acceleration is going to be pretty high, okay? That's this amount of acceleration is represented by the length of the vector here, okay? And the basketball has some mass m1, okay? Now, in this second part, he's now putting that same amount of force, applying that same amount of force onto a vehicle, trying to push the vehicle. Okay, the vehicle obviously has a higher mass, and so the acceleration of that vehicle is going to be much less than that of the basketball. Okay, so this is the idea of Newton's second law. So let's go ahead and do an example. Okay, this is example 5.2 in the textbook. It states, suppose that the net external force exerted on a lawnmower is 51 newtons, parallel to the ground. Okay, the mass of the mower is 24 kilograms. What is its acceleration? Okay, so we just found that net force is equal to mass times acceleration, okay, and we were given the net external force, and that was 51 newtons, okay. We were also given the mass of the lawnmower, which was 24 kilograms, okay. So to find our acceleration here, we can manipulate this equation with algebra and solve here. Okay, so our acceleration is going to be 51 over 24, which is 2.13 approximately. And We can check our units, make sure that they are in the correct units here. So remember that newtons is kilogram meters per second squared. Okay, that was given to us. So if we plug that in, we see the kilograms would cancel and we'd be left with the correct units here. Okay? All right, so that's that example. Let's do this example. This states the car shown in this figure here is moving at a constant speed. Okay, so we're looking at part A here. Okay. Which force is bigger, the friction force or the drag force? Okay, so this force or this force? And explain. Okay, so in this part, it states that V is constant. Okay, now if we think back to our relationship between velocity and acceleration, okay, acceleration is the derivative of velocity with respect to time. Okay, so if our velocity is some constant, I can just put C for constant. Okay, and we take our derivative here to find we take our derivative with respect to t of our constant, we'll just get 0 is our acceleration, right? That makes sense. Okay, so now when we're looking at forces, F equals m times a, doesn't matter what the mass is right now, our acceleration is 0, okay? So our overall net force is then 0 newtons. Okay, so part A then, the net force is 0, so these are going to be equal. Okay, that's what that means. So I'm going to say equal forces. All right, for part B, it says that the car is now accelerating to the right. Which force is bigger, the frictional force or the drag force? So now we have an overall acceleration. So we have acceleration of 10 meters per second squared. So this means we do have F net is not equal to 0 newtons. Okay. So it states that it's moving to the right. Okay. That means that this force is overcoming this force. So the frictional force is now overcoming the drag force. Okay, so we have F friction greater than F drag. Okay. All right, so let's move on to this next example. It says calculate the magnitude of force exerted by each of these rockets that is attached to this here. And this is called the thrust, or T, for the 4-rocket propulsion system here. Its initial acceleration is 49 meters per second squared. The mass of the system is 2,100 kilograms, and the force of friction opposing the motion is 650 newtons. Okay, so here we have the diagram that was initially given to us, and here is a free body diagram based on this drawing, okay, or based on the system. So we have our normal force, and we'll talk about that a little later. We have the weight of the object, okay? And then we have our frictional force, and then our 4 rockets, okay? The thrust of the 4 rockets, okay? So we want to find that thrust, okay? So we just care about what's going on in this x direction. We don't care about the y direction here, since the thrust is not in the y direction, just in the x direction. Okay? So we need to come up with an equation in order to solve for this. Okay, so we have F net is equal to MA, okay? And if we add up all of the forces, that's what we're going to do here, we get 1, 2, 3, 4 times T, okay? And I'm going to say that this is in the positive x direction, okay? And then I have minus F, my frictional force, minus F. Okay, so this is the equation that we will be using in order to solve this problem. Okay, so this is how we set it up. Remember that F net is equal to the sum of all forces. Okay, so this is where I'm getting that from. Equals mass times acceleration. Okay. All right. So now from this, I can go ahead and solve for T, just with a bit of algebra. So 4T equals MA plus F, or T equals MA plus F all over 4. And then we can plug those values in. My mass is 2,100 kilograms. My acceleration is 49 meters per second squared. Plus my force, my frictional force is 650 newtons. And all of that's going to be divided by 4. Okay, so I'll put that into my calculator real quick. And I get 2.59 times 10 to the 4th, and that is in newtons. Okay, we could probably round up to 2.6 times 10 to the 4th newtons. Okay, so this is now my thrust of each rocket. Okay. All right, so let's go ahead and move on to the idea of taking our force and putting it into component form. Okay, so each force, okay, can be broken down into x, y, and z components here. Okay, so we can calculate the force in the x direction, force in the y, and force in the z directions. Okay. Also, we need to understand the idea of momentum. So momentum is related to force in this way here. Okay, so force or net force is equal to the time derivative of the momentum, and momentum is equal to mass times velocity. Okay, so it will have, if we're wanting to know what units, we can say mass is in kilograms and velocity is in meters per second. Okay, so these are the units of P, or momentum. Okay, so this is equal to momentum. Okay. All right. So I can go ahead and try to get started on this example. This is example 5.5. We have a soccer ball that is kicked across the field by a player. It undergoes an acceleration given by this equation. We want to find the resultant force acting on the ball and the magnitude and direction of that resultant force. So we're going to have to go back and remember our vector notation and solving for vectors in order to find this force. So we'll continue in the next video.